Now that we understand some of the important concepts from probability theory, our goal is to make the connection between them and statistics. That is, we want to understand how we can use these probability ideas to better understand our data and the kinds of conclusions that we can make based on them. The goal of this lecture is to introduce an important concept that will help us make that connection. The concept we'll be talking about is the sampling distribution. Let's revisit the way we're looking at the inferential process. We have data in the real world and models in the theoretical world. Or the theoretical world could be a population and our data could be measured on a sample from the population. Either way, we have parameters in the theoretical world, which are features of the models or the population. And typically, we don't know the values of the parameters. We use the science of statistics to estimate them by a statistic calculated from our real-world data. We're going to think about this in a somewhat backwards way in this video. But going forward, it's important to understand what this backward thinking means for the real world. For now, we're going to assume that we know the theoretical world. That is, we know the parameters of our models or the population values. And then for a few situations, we're going to look at what the statistics we would use in the real world to estimate the parameters might look like. Of course, in real life, we only get one sample or set of data. But for now, we're exploring what all of the possible samples we could have gotten could be, so that we will be better able to understand that one sample that we'll actually get. Let's start with an example that we've already seen, flipping a coin 10 times, which is equally likely to come up heads or tails. This has a well-understood probability model in our theoretical world. The number of heads that can come up in 10 flips could be anything from 0 or 1 or 2 up to 10. And some of these values are more likely than others. Let's flip 10 coins a few times and see what we might get. We'll use this applet, which simulates coin flips, using an American penny. We'll set it to carry out 10 flips. For our first trial, we get 3 heads, which has been noted here in the plot. Let's try it again. We get another 3. So now there are 2 3s on the plot. This time we got 5 heads in our 10 flips. And now we got 4 heads. I'd like to do this a total of 1,000 times. We've already done 4, so I'll add in 996 more. The plot shows the frequency of all the observed counts of heads that we got. Not surprisingly, 5 heads happened most often. 4 and 6 also happened fairly often, and 0 and 10 heads didn't happen very often in our 1,000 trials of 10 flips of a coin. The probability distribution here is binomial 10 1/2, which looks like this using theoretical probability calculations. Suppose that the theoretical world parameter that we're interested in is the probability that a flipped coin comes up heads. We'll call this P. For 10 flips of the coin, the probability distribution then would be binomial 10P. Because we understand this model, we understand what might happen in the real world if we flipped a coin 10 times. Of course, in the real world, we get just one set of 10 flips. Our estimate of the parameter is the proportion of heads we got in our 10 flips. We'll call this P hat and calculate it as the number of heads observed divided by 10, the total number of flips. We use hats in statistics often to indicate statistics calculated from data to estimate theoretical world parameters. If we'd done another and another and another 10 flips, our real-world data would give various values of P hat each time, with probabilities following our binomial distribution. The fact that we don't get the same value each time means there is variability in our estimate. This variability is called sampling variability. Sampling variability is the variability we expect to see in a statistic that we're using to estimate a theoretical world parameter. Variability occurs because of the randomness in our data. The probability distribution of the estimator of the theoretical world parameter is called a sampling distribution. Sampling distributions are probability distributions with means or expected values and variances or standard deviations that we can calculate using the definitions and rules that Jeff showed earlier to calculate these quantities from probability distributions. We'll use these definitions and rules to calculate the expected value and variance for the sampling distribution for the estimate of the probability of heads from 10 flips of a coin, p hat. Earlier, Jeff showed that one coin flip can be modeled as a Bernoulli 1/2 random variable, which is either 1 or 0 with probability 1/2. And he showed that the expected value or long-term average of such a random variable is 1/2 also. If we generalize this to any situation where something happens or doesn't happen, heads or tails on a coin flip, red or silver in a flip of a beer cap, a randomly chosen person supports a government initiative or doesn't, with probability p that it happens, i.e. comes up 1 for our Bernoulli random variable, and then probability 1 minus p that it doesn't happen, or comes up 0 for our Bernoulli random variable, then the expected value or long-term average, using the formula Jeff gave us, is the sum over x of the possible values of x times their probability. For the Bernoulli p random variable, we get 0 times 1 minus p, or 1 times p, which works out to be p. If we think of 10 repeated coin flips, each as Bernoulli p random variables, with outcomes for these 10 Bernoulli random variables x1 through x10, and we estimate p, the probability of what we're interested in happening, as the number of times it happens divided by the number of experiments, 10 in this case, then this is x1 plus x2 plus x3 and so on plus x10 divided by 10, because, say it happens 4 times in our 10 experiments, then 4 of x1 through x10 will be 1 and the other 6 will be 0. And the sum of these 4 ones and 6 zeros will be 4, the number of times we get heads or whatever else we're interested in. So p hat, which is the sum of x1 through x10 divided by n, or 10, the number of experiments, is an average of 10 Bernoulli p random variables. And Jeff showed that for any n random variables with the same expected value, the expected value of the average is that same expected value. So the expected value of p hat is p. So in other words, we're using p hat, the calculated proportion of times that something happens in the real world, as our estimate of p, the theoretical probability that it happens, and the expected value or long-term average of our estimate is exactly what we're trying to estimate. Hopefully this sounds to you like a good property of an estimator. Indeed, such an estimator, which has expected value what it's trying to estimate, is called unbiased. So now we know that if we estimate the probability that something happens by p hat, the proportion of times it happens in our data, that the probability distribution of p hat, or its sampling distribution, has expected value p. So p hat seems to estimate what we want it to estimate, but in any one observed set of data, are we likely to be close to p? This depends on the variance of the sampling distribution. What we need to know now is the variance of p hat. Again, we'll look at one Bernoulli random variable, which is 1 or 0, or heads or tails, with probability p that it's a 1. Jeff showed us this formula for calculating the variance from a probability distribution, and for this Bernoulli random variable, we get p times 1 minus p. And in a previous video, Jeff showed that when we're taking the mean of a series of variables that have the same variance, the variance of the mean is the variance of the individual variables divided by n. So since p hat is a mean of 10 Bernoulli random variables, the variance of p hat is then p times 1 minus p over n, and the standard deviation is the square root of that. Note again how the variance and the standard deviation decrease with n. So the larger our sample size, that is, the more times we flip the coin or run the experiment, or the larger our sample size, the variability in the proportion of times the coin comes up heads or we observe what we're interested in decreases. That should be intuitive. We get more precise estimates with less variability with larger sample sizes. Here's an illustration of how the sampling distribution for p hat changes with sample size when the theoretical parameter p is 0.5. When the sample size is 10, as we've been working with, we have this binomial distribution for our sampling distribution of p hat, centered around our theoretical p of 0.5, since p hat is an unbiased estimator. Increasing the sample size to 40, or 4 times as large, cuts the standard deviation in half, since the standard deviation changes with root n. That gives us this distribution, still centered at 0.5, but more tightly clustered around it because of the smaller standard deviation. And increasing the sample size to 100 gives us this sampling distribution, even more tightly clustered around 0.5. To summarize some of this, when we're estimating a parameter that is a proportion or a probability of an event happening, and we know the value of the parameter is p, and we estimate it with p hat, the proportion of times that we observe the event in our data, then the probability distribution for the possible values p hat could be, in other words, its sampling distribution, has expected value p and standard deviation, the square root of p times 1 minus p divided by n. In working out some of these results, we looked at p hat as an average of Bernoulli random variables. Of course, we know a bit more about what happens in averages in the long run from a previous video. In particular, the larger the sample size, the closer an average gets to normally distributed. So for large sample sizes, a good estimate for the sampling distribution of p hat is the normal distribution with mean p and variance p times 1 minus p over n. We've looked a lot at the case where p equals 0.5, which gives us a nice symmetric sampling distribution. When p is further from 0.5, say closer to 0 or to 1, we need a sample size that's much larger before the normal distribution is a good approximation based on the central limit theorem. Let's look now at another case. Suppose our theoretical world model is a normal distribution. The normal distribution is a good model for quantitative data in many cases, so it will be important to us. A normal distribution has two parameters, its expected value, mu, and its variance, sigma squared, or you could talk about its standard deviation, sigma. For now, let's say the parameter that we're interested in is mu, the expected value. If our data are observations from this normal distribution, a natural choice to estimate the expected value is the average of our data values. We'll think of our data as observations of n values from this normal distribution with mean or expected value mu and variance sigma squared. We'll call these observations x1, x2 up to xn. Then our estimator of mu, our average of our data values, is x bar, the sum of the observations divided by n. Now, since x1 through xn all have mean mu, we saw previously that the expected value of the average is the same as the expected value of the individual variables if they all have the same expected value. What that means in this case is the expected value of x bar, the average, is mu. In other words, x bar is an unbiased estimator for mu. If x1 through xn all have the same variance, sigma squared, and they're independent of each other, we also previously saw that the variance of x bar is sigma squared over n, and then the standard deviation of x bar is sigma over the square root of n. What we've just done very quickly is derive two properties of the sampling distribution of x bar, the average of our data, which we're using to estimate mu, the expected value of our distribution in the theoretical world. Given that our theoretical world model is the normal mu sigma squared distribution, then the probability or sampling distribution of x bar has expected value mu and standard deviation sigma over root n. This is similar to the results we saw for p hat, our estimate of a proportion or probability. Like p hat, x bar is unbiased, and the larger our sample size n, the more precise estimates we get because of the smaller variance or standard deviation. We can use another applet to investigate the sampling distribution of x bar, the mean or average of our sample. Let's start with a theoretical probability model that has a normal distribution. This one has mean 16 and standard deviation 5. Now let's simulate some data. This time our data will be a sample of size 5 from our theoretical world model, the normal model. When we do this, the 5 data values in our sample are plotted here, and the mean or average of our sample data, the average of the 5 values we just randomly drew, is plotted here. We can see that the average is 16.4, which is quite close to our theoretical probability model value of 16. Let's take another sample of size 5. This one has a mean of 15.38. We can put our two means together in this plot, the distribution of means plot. The average of the means, each of which is a sample average from our samples of size 5, is 15.89. And if we do this 3 more times, we now have 5 samples of data, and we get 5 resulting possible values for what x bar, the mean of the sample values, can be. Now let's clear those so that we can take 1,000 samples. We don't see all our sample data anymore. It's too much for this plot. But we do now have a clear distribution of all of the 1,000 sample means. Note that it appears to have a normal distribution, and its mean is 16.05, very close to the 16 in our theoretical model, which of course is what we expect since we know that we have an unbiased estimator. Also, it is much less spread than we have in our theoretical model, also expected. The standard deviation of the distribution of means of samples of size 5 should be the theoretical model standard deviation divided by the square root of the sample size 5. And 5 divided by the square root of 5 is 2.236, and this is very close to the 2.30 we got for the standard deviation of our 1,000 samples. For our second example, let's increase the sample size to 25. We'll draw 1,000 samples again. For the 1,000 averages calculated from the samples of size 25 each, the mean, the overall average of these 1,000 means, these individual averages, is 16.01, extremely close to our theoretical model value of 16. And the standard deviation of the distribution of means with sample size 25 is 1.03, very close to 1/5 of the theoretical model standard deviation of 5. And again, this is exactly what we expect for a sample of size 25. So to recap, what we've seen when we start with a normal theoretical probability model and take samples of size n and calculate the mean for each sample, the mean of these means is the same as it was for the probability model. And the standard deviation of the distribution of means decreases from the value for the theoretical model by a factor which is the square root of the sample size. What happens if we start with a theoretical world model that isn't normal? Well, because we're working with means and we have the central limit theorem helping us here, we expect to see essentially the same properties. Let's use the skew distribution as our theoretical world model. It has a mean of 8.08 and a standard deviation of 6.22. We'll see what happens if we look at the sampling distribution of the mean, both for samples of size 5 and for samples of size 25, and we'll compare them on these two lower plots. The two sampling distributions for these samples of size 5 and 25 both have as their mean a value very close to our theoretical model value. For the theoretical model, remember it was 8.05, and for the distribution of samples of size 5, the mean is 8.05, and for samples of size 25, it's 8.04. So again, this illustrates that using the average as an estimator of the mean of a theoretical probability model is unbiased. That is, we expect to get what we're trying to estimate. Now let's talk about how the sampling distribution differs with the two sample sizes. The distribution for the larger samples, the samples of size 25, is less spread out since it has smaller standard deviation, which is what we expect. Remember, the standard deviation of the distribution of the means is the theoretical standard deviation divided by root n. So the larger n is, the less the spread. Also, the distribution for the smaller sample size is a little bit skewed. Less so than our theoretical model, but still a little bit. So the central limit theorem has only partially kicked in when the sample size is 5. But it looks like it's working quite well when n, the sample size, is 25, as the distribution for means of samples of size 25 looks quite symmetric and bell-shaped, like a normal distribution. P-hat, an estimator of a proportion or probability, and X-bar, an average, the estimator of the mean, are going to be the most important estimators going forward, and they're very well understood, as we've seen. So it's going to be possible for us to carry out inference for P and mu, what we're estimating with P-hat and X-bar, because the statistics we're going to use to estimate them, although they vary from sample to sample or from any measurement to any other measurement, they follow the structure of an understood probability distribution called the sampling distribution, which we've just studied. Knowing the sampling distribution is going to help us to quantify how much error there is in our estimates, and whether any observed differences can be explained plausibly by random chance, or if we'll need another explanation. And these are the important ideas of inference. We can look at the sampling distributions of estimators of other parameters of the theoretical world probability model, but the only other estimator we'll look at now is the estimator of the variance. Recall that when Jeff introduced the variance calculated from data, it was almost the average of the squared deviations from the mean, except it was divided by n-1 rather than n. This applet gives us the opportunity to explore the sampling distributions for the variance if we divide by n-1 or if we divide by n. Choosing variance from the menu gives the biased version, that is, divided by n. The version of variance in the applet with the u is the unbiased version, with n-1 in the denominator. We'll start again with a theoretical model that's a normal distribution with standard deviation 5, or more importantly, the variance is 25 then, which is what we're trying to estimate. Let's take samples of size 25, and we'll randomly simulate 1,000 data sets and compare the distributions of our two versions of the variance. Both distributions are a little right skewed, which, although we haven't studied it, it's a known property of the distribution of variances. So if we wanted to carry out inference on a variance, we'd need a right-skewed model and not a normal model. But let's focus on the center to see how well these variances are estimating the variance of the theoretical model. Again, the theoretical model had a variance of 25, and here we see the biased version has a mean of 23.91, not too far off from 25. But the unbiased version of the variance has a mean that is much closer. The mean of its distribution is 24.91. So that's a very short demonstration of why it's necessary to divide by n-1 when calculating the variance from data. What's coming next is that we're going to take some of these ideas about probability that we've been discussing and apply them to the analysis of data. And in particular, we'll focus a lot on inference for proportions and means. So why these two quantities in particular? Proportions and means are very important in a number of applications. Proportions in particular are used in polls, and they're also important in studies such as our HPV study, where we're interested in the proportion of people who developed an HPV infection depending on whether or not they were vaccinated. Means also have many applications. If we're comparing the error in age estimation between males and females, typically what we're looking at is whether or not the mean error differs between males and females. Or similarly, if we're comparing life expectancy among regions of the world, we might ask, is the mean life expectancy the same in these different regions? So the sampling distribution for proportion and means is going to be extremely important to us. And thankfully, we have some theoretical properties we've seen and the central limit theorem to help us.